All right, so in this section we're going to learn two new rules. One of them is the product rule. So this is going to be for functions that are multiplied together. And the other one's going to be the quotient rule. That's going to be for functions that are divided one by another. All right? So the first thing that we want to talk about is whether or not what we would like to see happen really works. In particular, is it true that if we multiply two functions together and then we take their derivative, that it would be the same as if we took the derivative of each one and then multiplied the result? So we're going to do an example to discuss whether or not that actually works for our example and see what happens. So the example we're going to use is not something where we absolutely would have to use a specific way of doing it, but we're going to explore what happens when we try. So in particular, what we're going to do is we're going to take our two functions, which is 4x to the 9th times x cubed, and we're going to simplify them by actually multiplying them together and then take their derivative. So if I multiply these together, what do I get? I'll start you out 4. What's next? I already have an x to the 9th, and I've got another x to the 3rd, so what's that give me? It's 12, right? You add the exponents. So this is 4x to the 12, and then I want to take the derivative of that. So what is the derivative of 4x to the 12? Perfect. And this really is the derivative. I mean, we simplified what's inside the parentheses first. We took the derivative afterwards. We know that this is correct. Absolutely is correct. Our question is whether or not we could have done it in reverse order and still gotten the same thing. So we're going to try that. We're going to do it in reverse order and see what happens. So what do I mean by reverse order? Well, I mean that I want to take them individually, the 4x to the 9th, and take the derivative. And I want to take the x cubed and take the derivative. And then I want to multiply them together afterwards and see what happens. Okay? So what's the derivative of 4x to the 9th? Perfect. 36x to the 8th. What's the derivative of x cubed? Fantastic. Now we want to multiply these together. So what happens when the 36 and the 3 are combined? It is 108. And what happens when the x to the 8th and the x squared are combined? Right. And is that the same thing as we had before? It's not. This and this are not equal. So back up here, the question is, are they equal? And the answer is no. It doesn't work. I showed a specific example where it failed. Now you might be looking at that and saying, well, but yeah, why would you even try? There was no need to do that to begin with on these functions. And you're right, there wasn't. But some functions, we don't have a choice to be able to really multiply them together first before we take a derivative. So we've got to have some other way of doing that. So we're going to do that with what's called the product rule. So let me show you what the product rule really does look like instead of what we had hoped it would look like. So the product rule has two components added together with addition. Okay? The two components have each of the individual functions times the other one's derivative. So we have one of the functions as it's written currently, f of x, times the derivative of the other one, and then we alternate that. We take the derivative of the f of x function and multiply by that by the original of the g of x function. And because this is addition, we could do this in either order. Because it's multiplication, we could do those in either order as well. So there's several varieties of how this could look. I could have just as easily done them in the other order, and it would be fine. The answer will still be the same. This is the order that I tend to work in, and let me kind of describe a little bit of why. It's not the order your book presents. The reason I like to work in this order is because the first step is simply writing down what I already have. I don't have to do anything. I know that first step, so I can always start the problem. And that's why I like that order of it. That's really all that there is to it. So if you're familiar and comfortable with doing a different order, fantastic. Go with the order you're familiar and comfortable with. But otherwise, this is the order I'm going to be showing on the board. Okay? So we're going to do an example where, again, it's not necessary that we do it in this pattern, but let me talk about why we might want to. So this function we could have done in the last section. What would have been the first step we would have had to do in section 2.3? Distribute. We would have had to distribute this out, right? So we're not going to distribute this out. We're going to do it with the product rule and going to give ourselves a little bit of practice at trying that. So my version of the product rule, the version I use, says I'm just going to rewrite the first piece, x squared plus 3. First piece rewritten. And then the second piece, I'm going to take its derivative. So what is the derivative of x squared minus 5? 2x. And then I'm going to have addition. And then I'm going to do this in the opposite order. And the next thing I'm going to do is I'm going to take the derivative right here of the first function. So now I need the derivative of x squared plus 3. That's 2x. Times the original of the second function, x squared minus 5. Now we're very quickly approaching something in your syllabus that's called the Derivatives Basic Skills Quiz. We haven't talked about that since the first day of class, but we are approaching that. When we get to that point, you will be asked to find a bunch of derivatives. Some of them will be using product rules. And you're not expected to simplify anything. So on that particular quiz, this would be your answer and you'd stop. Okay? So at that point, we'll work on the complex issue of just focusing on the derivatives, not the algebra that follows them. In your homework, we're going to work on the algebra that follows them as well. So we're going to work on both components. So at this point, we're going to simplify what we have, which means we are going to distribute things out. So I'm going to take my 2x times the x squared to give me 2x cubed. And then my 2x times my 3, 6x, right? And then we're going to do the same thing over here, 2x times x squared to give me 2x cubed. And 2x times negative 5 to give me negative 10x. And then we can combine like terms. So what would we get for our final answer on this one? 4x cubed minus 4x. Perfect. Good job. So that's what you're going to be doing on your homework, is getting to the point where it's all cleaned up and simplified. Yeah?
On, like, when we take the quiz, would we get it wrong if we went ahead and, like, multiplied it out?
So here's the deal. You'll get it wrong if when you multiply it out you make an error,
Okay.
which is why it's to your best in your best interest not to do that.
Okay.
Because the more work you do in a particular problem, the more likely it is you're going to make an error, just naturally, right? So yeah, it will say do not simplify, big bold reminder to yourself to do that.
Like, doesn't say we're, like, freaking out about this
Yeah,
quiz.
no, seriously, when you, and remember this quiz, actually you have multiple attempts to keep reworking it, so there's no reason to freak out on the quiz anyway, honestly, because you're going to have a chance to do it again if you make mistakes. Okay? All right, let's try another one. Now, on this particular problem, again, we could distribute this out, we could multiply it out, and that's fine, but this one's even messier than the last one, right? It's kind of ugly because it's not a polynomial. I've got an x to the 3 halves involved here. That's kind of ugly. So we're going to use the product rule again. That's what we're working on in this section. We'll very quickly get to ones where we couldn't do it any other way. But for this one, we actually could do it any other way. This one tells us to use the product rule. So first step is to do what?
Just write the first one.
Just write the first one however it is, you betcha. All right, now somebody give me the derivative of the second piece. Good, 4x cubed, excellent. Now I need the derivative of the first piece. So what is the derivative of x to the 3 halves minus 4? I'm sorry, minus 4x. Good, 3 halves, x to the 1 half, minus 4. Excellent. And then what do I do? I rewrite the second piece, x to the 4th minus 2. And again, if you were working the basic skills quiz, what you're going to do, you'd stop there. You wouldn't go any further. Okay? In particular, also, it's the algebra that makes the problems take a long time. So the derivative part of it is usually fairly quick, at least by comparison to the algebra that follows. So you don't want to do more than you have to for that purpose as well. All right, so for what we're doing right now, we're going to simplify the mess. We're going to clean it up, okay? And just so you know, there's going to be a reason why we want these cleaned up in the future. We aren't really talking about that point today, but there is good reason for wanting to clean these up later. So for right now, we're just going to simplify this out. So when I take 4x cubed times x to the 3 halves, I'm going to get a 4. What is my x value going to give me? I mean, what's the exponent? 9 over 2. How did you get 9 over 2? Somebody explain. You're adding,
3 halves.
yeah, the exponents, right? So we're adding the exponents together, so the 3 halves plus the 3. Good. The next one is going to be 4x times 4x cubed, which gives me 16x to the 4th. Okay, so that one was the easy distribution, that is, compared to the next one, because what's going on in the next one that makes this harder? This one harder. Yeah, I'm going to actually have to foil. I'm going to get 4 pieces of the puzzle when I'm done, right? All right, so let's do the first terms together. I have 3 halves, x to the 1/2 times x to the 4th. So I'm going to get a 3 halves. What else am I going to get?
9/2.
Oh, goodness, we got another 9/2, don't we? So that's nice. We're going to be able to combine something. So those are my first terms. FOIL says I should do the outer terms next, although your order doesn't really matter, but we'll go in that order. So I've got another 3 halves, x to the 1/2 times the -2 now. So the 3 halves times the -2 gives me, yeah, -3 actually, right? And then I've still got the x to the 1/2 that's already there. Then we're going to do our inside terms. Those are probably the easiest ones on this one. Well, the last ones as well. So what's my inside term going to give me?
-4.
Excellent. You guys are doing great on your algebra. I'm very pleased. All right, and then our last terms, right? So the 4 times the -2 to give me -4 times -2, +8. And then we combine like terms. So there's not a lot that can combine here. In fact, maybe only 2 things, isn't there? Is that all I'm seeing? All you're seeing? Oops, not that one. This one? And they aren't especially friendly to combine because one of them is a fraction and one of them is a whole number. But I have an x to the 9th. I've got 4, and then I've got 3 halves. So how much is that? 11/2. It's 11 halves. And you can use your calculator to get that as well. And if you really want to put that in decimal form, you could. I mean, it wouldn't hurt anything because it is a terminating decimal. Oh, there is one more thing I can combine. I didn't see it. Isn't there? Those two. Yeah, there you go. What is that one going to give me? Right, -20 x to the 4th. Perfect. Now what? I think the other 2 pieces are just going to be what they are, right?
Yeah.
3x to the 1/2 and +8. So this is my derivative for the original f of x function. All right. We're going to move on to the quotient rule before we get into some of the other ones. I have one more later on, but we're going to use the quotient rule next. So the quotient rule is asking the same question. If I take a fraction and I take its derivative, is it the same thing as taking the derivative of the numerator, the derivative of the denominator, and then putting them into the fraction form? So we're going to explore that option with a very similar function to what we had before, except we're going to do a quotient with them instead of a product. So the first thing I'm going to do is, like I did before, I'm going to write f of x, 4x to the 9th, over g of x, x cubed. And we're actually going to simplify that first and then take the derivative. So if I simplify this first, what do I get?
4x to the 6th.
Perfect, 4x to the 6th. And how did we get 6, just as a reminder?
The x cubed cancels with the x to the 9th.
Yeah, and sort of a shortcut way of thinking about it is we subtract the exponents, right? But you're right, it's a cancellation feature, right? Okay, and then we're going to take the derivative of that. So what is the derivative of 4x to the 6th? 24x to the 5th. All right, so this is really, really the answer to this problem, for sure, without a doubt. The question is, could we have gotten there by doing the derivatives of the top and bottom separately to begin with and then divided them? So that's the question we're going to explore next. If I did 4x to the 9th on top and took the derivative, and on bottom I did the x cubed and took the derivative, what would happen? So what's the derivative of 4x to the 9th?
36x to the 8th.
Perfect, 36x to the 8th. And then what's the derivative of x cubed? Good, 3x squared. So now we're going to simplify this one after the fact. So the 36 and the 3 become a 12. And the x to the 8th over the x squared become a x to the 6th. This one's 6. Subtract the exponents, right? Yeah. And what happened? They're not equal. I mean, this is not the same as this one. Not equal. So up here, the question of does this work? The answer is no, it does not work. It's just not the same. It's not going to give me the same answer. So if it's not giving me the same answer, that's not the right rule for the quotient rule. So let me show you what the quotient rule is. I'll let you write it down, and then I'll give you at least a couple of mnemonic device kind of things to help you remember it, okay? So this actually is the quotient rule. So what you see right here is you see that this is the denominator, this is the derivative of the numerator, and then you reverse it, numerator, derivative of the denominator. It looks very similar to the product rule, except what? There is subtraction up here. So now the order matters. You can't just flip-flop them. If you do, you're going to be off by a negative, okay? So you can't flip-flop the order on this. You really need the order as it is. And then this is divided by the denominator squared. So there are two mnemonic devices, obviously very, very similar. The only difference in what I wrote down is what I wrote on bottom, right? Okay, so the first one's more technically correct, but the second one's the one that I actually learned when I was learning calculus. All right, so the first one calls the numerator high and the denominator low. So what you write down, or what you can remember, is this is low D high minus high D low all over low low. Cutesy thing. If you don't like it, just ignore it, okay? But for some people, it helps to have sort of something to think about that's not in terms of all of the equation stuff we use all the time. The D is telling you derivatives, so when you see the thing that says D high and D low, that's an L low, not a lie. D low, that's telling you derivative of that piece, okay? The other one is the one that I was taught, so it says something like this. It says Hody high minus Heidi ho all over ho ho. And I think that that was really coming out of the fact that at the time when I would have been learning this was when I don't remember what the actual show was called, but it was the Tim the Toolman Taylor Home Improvement. Thank you very much. That was really popular, and so his neighbor always says Heidi ho. That's the thing. So they're just cutesy ways of remembering it. That's all it is. So if you like one of those and want to remember it that way, that's great. If not, that's fine too. We're going to actually take a look at solving some equations now with this. Now, the examples for these, 3, 4, and for 5, all force us to do this. There is no way to simplify this particular expression unless you want to do like long division or something like that, and you're still going to end up with a fraction at the end and it's a mess. So you have to use the quotient rule. The two examples that I created for the product rule, you could have used the product rule, or you maybe didn't have to use the product rule. Here you have to use quotient rule. There's not another choice, okay? So the quotient rule says that what I'm going to do is I'm first going to rewrite the denominator. That's 5t minus 3. Rewrite the denominator. And then I'm going, which I'll use the denominator in black and I'll use my numerator in red. And then I'm going to take the derivative of the numerator. So what is the derivative of the numerator? 2t is correct. And then what sign goes between them? A negative sign. Then I return back to the denominator, or, well, the way that I have it written. Then I write the numerator, which is t squared plus 4. This you could do in either order right now. And then I take the derivative of the denominator. So what's the derivative of the denominator? 5. And all of this is written over what?
5t minus 3 squared.
Right, 5t minus 3, the denominator, squared. Now if you were working on the derivatives quiz, you'd stop right there. Okay? Now in particular, even now, you're not going to do anything with that denominator to FOIL that out. You're not going to multiply that. That doesn't make anything simpler. The only reason that the distributing of the numerator is helpful is because things tend to combine when you're done. Okay, you end up with fewer terms, less mess than you already have. But the denominator's not really a mess. It's in a nice, compact, factored form. It's really helpful as it is. So you're not going to mess with the denominator. It's just not helpful. Okay, but we are going to simplify the numerator for the time being because that has a chance of being helpful for some things we're going to see down the road. So we're going to FOIL or distribute. In this case, we're not foiling, we're distributing this out. So I need 2t times 5t, which gives me 10t squared. And then 2t times negative 3, negative 6t. Very good. And then on the other one, I'm going to have 5 times t squared, 5t squared, and I've got a negative in front here, so this is negative 5t squared. And I'm going to have 5 times 4, which is 20, and again, the negative in front of it makes it a negative 20. Now, every step needs to have the denominator rewritten. You're not simplifying anything out on it, but you don't want to leave it off because that would make it unequal to the actual g prime of t function. And then you're going to combine what you can together. So 10t squared, and then what?
5t squared, I think.
Oh, did I leave a squared off earlier? I sure did. Thank you. So it's not 10t squared, is it? What should it be? 5t squared. Thank you. I missed that one. And then what's next? Minus 6t. And minus 20. Over 5t minus 3 squared. And that's actually where we stop. T's are not my favorite variable to use. S's are worse, actually, but T's are not great. It will probably be helpful for you, me, and the grader if you do some kind of a curly underneath your T so that your T's don't look like your plus signs. Just whatever you do, make sure that your T's and your plus signs don't get confused, both for you and for whoever's looking at your work, okay? So try to be careful with that. S's are worse, though, I promise. All right, let's try another one. Is everybody good on that one? Any questions? You're good? You have a question, Darby?
How do you know to stop right there?
The only thing that's possible at this point would be if the numerator factored. It doesn't happen very often that it will factor. When we get to the point of wanting to discuss that issue, we may attempt to factor it to see, but right now it's not necessary. So we're just going to get to the point where the numerator is all distributed out, cleaned up, combined, and the denominator stays in its factored form. That's the goal of where we want our derivative to end when we're done. Okay? All right, let's try another one. This one is less pretty than the one before. Do you say less pretty? Yes, less pretty. All right, so at the very least right now, we need to rewrite this just a touch in order to help us to take a derivative. What might be helpful to have rewritten in a different way? The minus 2 is actually just very friendly. I don't want to mess with him. Yeah, the part with the square root's not especially helpful as it's currently written. How can I rewrite it using rules that we've already discussed? Right, 6x to the 1/2. We have a power rule, so I know what to deal with in terms of powers. I like the minus 2 on the end because what's the derivative of minus 2? So it doesn't really matter in the slightest, does it? It's actually not going to have any component in its of it in our final answer, so that's actually quite friendly. All right, so our derivative starts out by doing what? Writing the denominator. Thank you. So it's 5x squared. And then what do I need to do? Take the derivative of the numerator. All right, so the 3 part goes away. I just need the derivative of the negative 6x to the 1/2. So what's that? Minus 3. X to the negative 1/2. Right, so it's 1/2 minus 1, or negative 1/2. And then what comes next? Minus. And then what? 10x. Okay, so you did the derivative of the denominator next. That'll work. And then what? Numerator. We're just going to rewrite the numerator. So 3 minus 6x to the 1/2. And all of this is over what? 5x squared squared. Okay. And I'm going to actually throw one extra piece of information in here just to remind us. At the end here it says minus 0 because the derivative, minus or plus, whatever you want to write down, the derivative of the 2 is nothing. So if you just leave that off, that's fine too. But yeah, you don't have to write it. I just want to make sure that you guys realize that I didn't forget about it. It's just actually a 0 derivative. So if you don't write it, you're fine. All right, we're going to clean the numerator up. Now this is one of those cases, Darby, when we're actually going to simplify the denominator because simplifying it actually isn't difficult and it cleans it up. Okay, so we're going to go ahead and simplify the denominator on this one. We didn't on the last one because simplifying it, quote unquote, would actually make it messier. We don't want to make it messier. Our goal is to keep it clean. So let's simplify this numerator. What do I get when I do 5x squared times negative 3x to the 1/2? What's the coefficient? Negative 15. Thank you, Paula. What is going to be my exponent on x? 3 halves. So negative 15x to the 3 halves. All right. Now I'm going to have to distribute the 10x through things. So what is 10x times 3? 30x, and I've got the negative here on the outside, so this is negative 30x. Now, what is 10x times negative 6x to the 1/2?
60x.
So I've got 60x to the 3 halves. It would be negative, but then I've got another negative in front, so this one will actually end up being positive because there's 2 negatives involved. And all of this gets divided by what? 25x to the 4th. Now, this is a very strange situation. There is something in common in every single term there. What is it?
5x.
Yeah, there's a 5 and there's an x, both, right? So let's do the 5 part first. We're just going to divide everything by 5. Okay, that will simplify what's there. So 15 divided by 5 would be 3, and it's negative. Negative 30 divided by 5. Is there a problem, Dean? Do you have a question?
I was wondering if you should first subtract the 15x to the 3 over 2 with the 60x. So first, I just wasn't sure.
Oh, like at the very end?
Like reducing it, because
Like just combine it.
Yeah. With which pieces? Which are you looking at?
15 and 60. So negative 15x.
Oh, you could. You could. Yeah, it wouldn't matter if you did it in that order. Yeah, you definitely could do that. I've already started marking mine in red, but we could definitely do it in the opposite order, and you're going to get the same answer. Yeah. Yeah, that's true. All right, let's go ahead and simplify the 5 since we were in the middle of it. What is negative 30 divided by 5? Negative 6, right? And then 60 divided by 5? 12, very good. And then 25 divided by 5 is 5, right. And trying to think what order. You know what? Let me write this down because I'm going to get a mess going on here. And let's combine the ones that Dean just mentioned. So this is negative 3x to the 3 halves, and I've got 12x to the 3 halves. So how much is that? 9. So this is 9x to the 3 halves. And then I've got minus 6x. And I've got this over 5x to the 4th. We've got one more step. We still have x in every term, right? So we're going to divide every term by x, just like we divided every term by 5. So if you were to divide, I'll do the first one last. We're going to do the other two first. So if I divide 6x by x, what do I get? That's just 6. What if I divide 5x to the 4th by x? That's 5x cubed. Those are the easiest two. What if I divide 9x to the 3 halves by x? It's an 9, and then it's x to the 1/2. And you can remind yourself that it's subtraction of exponents if that helps. So 3 halves minus 1 is going to give you 1/2. Or you could recognize that x to the 3 halves means x to the 1.5. So the x to the 1 is what's simplifying, and the 0.5 is left. That's another way to think about it. Anyway, you look at that. This is your final answer. Any questions on that one? So carefully read the directions. Don't say it out loud yet, but carefully read the directions for number 5. And then once everybody's had a chance to do that, I'm going to ask you what the difference is in this question than the last ones. But don't answer out loud. Give everybody a chance to read. How's this question different than the last two we just did?
You have to find an equation of the line.
Yeah, our answer at the end is going to be the equation of a line. So we'll write this down at first as a reminder to ourselves. We're going to have this kind of an answer that we simplify when we're done. One of those pieces of information we already know. What piece do we know? We know the x value. Yeah. So the x value, x1, is 1 in this case. Excellent. So we need to find 2 more pieces of information. We need to find y1, and we need to find m. And we actually could do that in either order. just to emphasize to you that it doesn't matter, let's find y1 first this time. How do we find y1? You plug in the number 1 for x that you were given. So this is going to find y1, and it's found by plugging in the value for 1 of x that we were given. So in particular, if you plug the number in as the number 1, this one you can do in algebra real quick in your head, you're going to get 4 over 2, which gives you 2. So that one was actually really clean, especially compared to the last one we did. So that one actually gives me the number 2 right here. You're looking confused, Kaylee. Are you okay?
I'm good.
Okay. Does anybody have any questions on that step? All right. So our last step to do then is to find m. M is found by doing what? Taking the derivative. So we need to find the derivative of f. All right, so the derivative here is a quotient rule because I've got a numerator and a denominator. So what is the first part of the quotient rule?
Just writing the denominator.
Writing the denominator. And then the second part of the quotient rule is to do what?
Take the derivative of the numerator.
All right, so what is the derivative of the numerator?
1.
1. It is. What sign comes next?
Negative.
A negative sign, a subtraction sign. Next, what am I going to do?
Write the numerator.
Okay, I can write the numerator, x plus 3, and then
Derivative of the denominator.
derivative of the denominator. I think you've done this before, Matt, have you?
Yeah.
Yeah, okay. What's the derivative of the of the denominator? 2x. 2x. And we're going to write this all over x squared plus 1 squared. Exactly. Now, if you wanted to, and if this were complicated and messy, you could not simplify this and just stick the number in everywhere you need to go and simplify it with numbers in it. You could do that. It wouldn't hurt anything if you did. This one cleans up pretty nice and easily for us, so I'm going to go ahead and simplify the actual expression we're given, or that we're currently working with, but we wouldn't have to because we really don't need to find the derivative. We need to find the derivative evaluated at x equal 1, right? That's really what we need. So I'm going to clean this one up just because it cleans up quickly. The first one especially because I'm multiplying by 1, right? Yeah, nothing to that one. So I've got x squared plus 1. The second one is also pretty clean. I've got 2x times x, which gives me 2x squared, and then I've got a negative at front, so this is negative 2x squared. Then I have 2x times 3, which gives me 6x, and then the negative at the front, so negative 6x. Good job. Again, there's no reason to simplify that denominator, so we're not going to distribute it out or anything. And we'll just combine what we've got. So what do we have on the numerator that we'll combine? X squared and the negative 2x squared to give me negative x squared. And then minus 6x plus 1. And then x squared plus 1 squared. All right, so this is my function f prime of x. But again, we didn't really want f prime of x. We want f prime of what? 1, because that's the x value, or a value is how they described it that we were given. So if you take your calculator and plug in the number 1, or again, this one's not too bad to just do it in your head because it's all polynomials. But you actually would have negative 1. You end up with plus 6 because you've got negative 6 and negative 1, and then plus a 1, over 1 squared plus 1, which would be 2, and then squared. So I think you end up with 6 over 4, which simplifies to what? 3 over 2, or you can write 1.5 if you really like decimals instead. So right here, this is 3 over 2. Does that look okay? And we're going to use this information then, and we'll go to the next screen to simplify and clean it up.
Why is it plus 6?
Do I have something written wrong?
If it's negative 6 times positive 1.
It was positive 1, not negative 1. You're right. I was using a negative. Thank you.
And it's 1 plus first one is positive.
No, the first one is negative because of the negative in front right here. So that one will stay negative. So let's fix this up here. Thanks for catching that. Negative 3/2. Perfect. This is why I have to do this in front of you guys. If I were doing it in my office by myself, I'd be making all kinds of mistakes and never know it, right? It'd be bad. All right, so we have y minus 2 equals, what was it? Negative 3, was it negative? Yeah, negative 3 halves. And then x minus 1. Perfect. All right, so we have y minus 2 equals negative 3 halves x plus 3 halves. And then what? Add the 2, you're right. So this is y equals negative 3 halves x, and then what are we going to be adding here? Yeah, 4 over 2 plus 3 over 2 for a grand total of 7 over 2. That's right, good job. All right, so that's what we get. Yes,
Back to the last one.
you bet.